Problem 2 is inspired by a problem the seniors encountered in a senior design problem a few years ago, and I've adapted it to an automatically closing microprocessor-controlled mini-blind system. This circuit is an analog front end that measures when there's light or when it's dark. And the idea is that if it's dark, a microcontroller will close the blinds, and if it's light, the microcontroller will open the blinds. So this is the circuit here, and it could be just this circuit with a cadmium sulfide resistor. That's 100 ohms if it's light, 10 kilo ohms if it's dark. It's made with a voltage divider down here, and then this provides some sort of variable voltage that's dependent upon the ambient light. So if it's very bright, this becomes a very small resistor compared to this. So this is much closer to 5 volts, it gets pulled high. And if it's dark, it's a much bigger resistor, and so there's less resistance to ground, and so it goes down close to zero. And you could put that into the microcontroller's analog input. But instead, we're going to save some processing power and convert this analog signal into a digital signal. So we create this comparator over here, and it's going to compare the input to a 2.5 volt signal. When it's light, this wire becomes close to 5 volts. If this were an op-amp instead of a comparator, when this voltage is higher than this, when it's light out, the op-amp would go high, infinitely high if there's no feedback. In fact, it would go up to the 5 volt maximum. But this is a comparator, and so instead of going high, the comparator disconnects. When it disconnects, now the comparator acts as if it isn't there, and this line gets pulled up through this resistor to 5 volts. So when it's light, it's high. When it's dark, this line is lower in voltage than this. If this was an op-amp, it would go down to negative infinity volts. In fact, it would be limited by its lower voltage. And a comparator will short the output directly to ground. So when it's dark, it's 0 volts, and when it's bright, it's 5 volts. Now this circuit works great when it's exposed to sunlight, and it works great in an office when lit by incandescent lamps. But it doesn't work when it's in an office lit by fluorescent lights, and why? So when it's in an office, you've got these fluorescent lights, and these fluorescent lights actually flicker very quickly. Now if this is the voltage, and the voltage is at 60 hertz, how fast does it flicker? In other words, in 1 second. In other words, this distance is 1/60th of a second. And it flickers on and off every time that the voltage is 0. So if the voltage is at 60 hertz, it's going to flicker at 120 hertz. Another way of looking at this is to say, what is the power? What's the voltage times the current? And assuming that that fluorescent light looks like a resistor, that would be equal to the voltage times I, which would be voltage divided by resistance. So that would be voltage squared over resistance. So we don't know what that resistance is. But when you square your cosine, that cosine is going to look like some omega t. We're not quite sure what that omega is, but that gives you a trigonometric identity of 1 plus cosine of 2 omega t. So if the original omega was 60 hertz of your voltage, you've got twice that for your power, and of course it's your power that produces light, so it's going to flicker quite quickly at 120 hertz. So the reason is power flickers at 120 hertz, exactly according to this equation. So what kind of filter would prevent this? Well, would you want a low pass, band stop, or high pass? One way to think about it is we're most interested in this power waveform because the light's proportional to power. And if we were to graph that power waveform as a function of frequency, we'd have this, which gives us a DC term, and this, which gives us another term up at 120 hertz. Now I'm drawing it in hertz. I could have just as well multiplied by 2 pi and do it in radians per second. But I think from this it's clear that it's the 120 hertz that we want to eliminate, and it's this average value that we want to pass. So we want a filter that passes low frequencies and that cuts off high frequencies. So that's a low pass filter. Where would you put the filter, and what order would you use? Well, if you put it here, that would definitely filter your input. The problem is that the output of a filter is an analog signal. It's not a digital signal. It's not 0 or 5 volts. It's something in between. And you want to give your microcontroller a DC value, so you don't want it there. Instead, you want to put it right here. And then that will pass that DC value and block the rapidly changing 120 hertz value. So where would you put the filter? Before that non-inverting input of the comparator. What would you design its cutoff frequency to be? Well, you can kind of see from this diagram, you want it to be greater than 0, and you want it to be less than 120. That's a pretty big range. Where should it be put? This is where engineering judgment comes in. Let's decide how much we want this signal blocked, how much of 120 hertz we want blocked. Let's say arbitrarily, we want to cut this signal down by 99%, so we want to just pass 1% of the signal at 120 hertz. There are many ways to build this filter. You could build it out of a second order, a third order, a fourth order filter like you did for your lab project, but it's so much easier building a first order filter because a first order filter does not require an op-amp. It just requires a resistor and a capacitor. And that's it. This is your input, that's your output. Really high frequencies, you can see everything gets grounded. Really low frequencies, this looks like an open and it goes through. And if you analyze this as a voltage divider, you can find your H of S relating your input to your output will be some constant over S plus 1 over RC, where this is your R and this is your C. Easy to design. What's the numerator? Turns out that at 0 frequencies, this passes it, so the numerator will be 1 over RC. You could have calculated that using a voltage divider, though, and replacing the impedance of C with 1 over SC. And then your H of S, derived from first principles, would be this guy, 1 over SC, divided by the sum of the two, R plus 1 over SC, multiplying top and bottom by S over R gives you this. So if we can design it using a first order filter, we want to do it, because then we can design it using just passive components, a resistor and a capacitor, and we don't need to add a new op-amp to the system. If we designed it as a first order system, it will drop our input at minus 20 dB per decade after the cutoff frequency. So if we want to block 99% of our 120 hertz undesired signal, if it's a first order, we'd have to make the cutoff frequency at 1.2 hertz. And this way at 12 hertz, that's 1 decade, and we'll block 90% of our signal at 12 hertz. At 120 hertz will be our critical frequency. That's our next decade. And it will block only negative 3 dB at its critical frequency. 1 decade lower, minus 20 dB. Another decade lower, minus 40 dB. And so at 1.2 hertz, it'll be 40 dB down, which corresponds to 0.01. So that would be a good cutoff frequency to use, 1.2 hertz. Although acceptable would be really anything in this region. Why would 10 kilohertz be a poor choice for the filter cutoff frequency? Well, 10 kilohertz is way back there, way over here. That would mean that your filter response would look something like this. And that wouldn't cut off any of your 120 hertz signal that you want to reduce. So it's a bad choice because that passes your 120 hertz signal. Why would 100 microhertz be a poor choice for a filter cutoff frequency? Well, at first blush, that seems like it's a great cutoff frequency. That cutoff frequency would be over here, and that would definitely take out your 120 hertz. I mean, at 100 microhertz, 1 decade above that is 1 millihertz. Then you've got 10 millis, 100 millis, 1 hertz, 10 hertz, 100 hertz, that's pretty close to 120, so that's 1, 2, 3, 4, 5, 6 decades. So even with a first order filter, 100 microhertz would give you 6 times 20 dB per decade drop. This would give you a 120 decibel decrease, minus 120 decibels of your input signal. That's as close to zero as you can possibly get, but yet it would still pass your DC component. This turns out to be a terrible choice for a cutoff frequency if you look at things from the time domain, because 100 microhertz corresponds to a time period, which is 1 over f, of 1 over, 100 micros is, that's the same thing as 0.1 millis. So 1 over 0.1 is 10, 1 over a milli is a k. The time period of this circuit corresponds to about 10,000 seconds. And that means that this input will so slowly change, if it's got such a low cutoff frequency, that it will take about 10,000 seconds for it to mostly stabilize. That's its time period. And 10 kiloseconds corresponds to about 3 hours. So it would take 3 hours to react to changes. For this particular system, you don't want your blinds to close 3 hours after it gets dark, so you want to create a faster time response. Now, though I chose 1.2 hertz up here, if you wrote down 0.1 hertz, that's fine. That might take 10 seconds to respond, no problem. If you wrote down 10 hertz, 12 hertz, that would be fine too. That's only 1 decade down from 120. So instead of reducing things by 40 dB, you'd be dropping it down by 20 dB. That's still 90%, right? Negative 20 dB is 0.1, so it would multiply your 120 hertz signal by 0.1. So only 10% would get through, and that's 90% reduction. That would be fine. So really, anything in this region would be a perfectly reasonable choice for a cutoff frequency.